Hey, focus. Here we go. This isn't that tough, but it is necessary as an introduction to what we're going to be doing with polygons, which is finding the area of polygons. That's really our whole focus of this J2, is just finding the area of polygons. So we have to get used to the idea of working with polygons again, other than just triangles and rectangles and squares and other types of quadrilaterals. What are we going to do with pentagons, hexagons, octagons, whatever? Now, one of the things we're going to keep talking about is the sum of the interior angles, because it's going to become important. So we know that a triangle, if we add up all the interior angles, we get 180 degrees, right? And for a quadrilateral, we add up the interior angles. What do we get? 360. Okay? So for 3, we had 180. For 4, we have 360. How many degrees are going to be for 5? If I add up all the angles of a pentagon, how many degrees are we going to have? Well, let's think about this for a second. In a triangle, how many triangles do we have? One triangle. Okay? Okay? Whoa, weird thing happened. Okay. In a quadrilateral, how many triangles do we have? 2 triangles. Each one is 180, therefore 360. In a pentagon, how many triangles do I have? 3. So each triangle is 180, right? So that's 540. In a hexagon, how many triangles? Right. Okay, so that's 720 degrees. In fact, what do we notice about the relationship between the number of sides and the number of triangles? When we had 3 sides, there was 1 triangle. When we had 4 sides, there were 2 triangles. When there are 5 sides, there are 3 triangles. When we have 6 sides, there are 4 triangles. Every time we add a side, how many triangles do we add? 1 more triangle. What's the relationship between the number of sides and the number of triangles? Number of triangles is always 2 less. Yes. Number of triangles is always 2 less than the number of sides. So if I have n sides, I have number of triangles, n minus 2 times 180 degrees per triangle. Okay? So that's where that formula comes from that you put in your note card, and that's going to be the important formula. That's the sum of the interior angles of a polygon. If I add up all the angles, all the interior angles, that's how I find the sum for all the interior angles. Exterior angles I'm not going to worry about so much here. We can talk about it for a second. But let's actually say, okay, if that's the sum of the interior angles, what if, and let's do a hexagon here, okay? What would the measure of each angle be if it's a regular polygon? And pretty much we're only going to be working with regular polygons, which makes life a little bit easier. What does it mean for a polygon to be regular again? Who can remind me of that? Polygon is regular. It means it's got 2 very special properties. Yes. Well, closed is for all polygons. Yes, that would be a property. That's not one of the special ones we're looking for. Yeah. All sides are congruent. It's equilateral. All sides are congruent, and all angles congruent, which we call Disappointment. You're going to break me? No. As God is my witness, you will never be ignorant again. Stop, why?
Because you're wasting time.
No, it's a Gone with the Wind quote. So equiangular. Equiangular. If all the angles are equal, we call it equiangular. It's not really difficult to figure out. Okay? And the question then becomes, find the measure of each angle. How did you find that? Through math. Can you explain the math to me? Yeah, because we find the sum divided by the number of sides, or the number of angles in this case. So we can find the measure of each angle is 120. And then what's going to happen when I start finding the center of the polygon and start drawing in these isosceles triangles, what's going to happen to each one of those 120s? They're going to be divided equally, right? And so that this is going to be 60, and this is going to be 60. And guess what this angle is going to be in the hexagon too? 60. They're all equilateral triangles inside. That's kind of special. And guess what happens when I drop down the altitude? What kind of triangle do we have? We have a 30, 60, 90 triangle, don't we?
Wow.
Okay? So you start seeing how all these things are going to work together. Now, does that always happen in every polygon? No, just in every regular hexagon. All right? If I deal, say, with, I don't know, how about nonagon? 9 sides. Okay? So there's 9-side polygon. Okay? So what's the sum going to be? Give me the formula. Oh, wait. How many sides? 9. 9 minus 2 times 180. So that's 7 times 180, which is 1260? Okay. So each angle, if we divide them by, so 1260 divided by 9 gives me
140.
Really? Perfectly?
Yes.
Okay, excellent. Okay. Okay. Guys, settle. Okay. So again, if I start drawing in this triangle to find out things about, because of course we always work by breaking it down. Now what's my right triangle here? What's the measure of this angle going to be? 70 degrees. Okay, and I could now use SOHCAHTOA within that triangle because that's not a special triangle, but it's still a right triangle. And now I can do all sorts of things with SOHCAHTOA to find out what's going on with the triangle as well. So this is kind of the process we're working with, which is why we start out with by talking about the sum of the interior angles of the polygon, because it helps us set up these smaller triangles within the polygon. Remember, we don't ever really try to do the whole polygon at once. We get larger quadrilaterals, we start breaking it into triangles. And we start breaking those isosceles triangles into right triangles. And we are not even dealing with polygons that are not regular. I mean, we could do, if we start dealing with irregular polygons, then it gets much more difficult. Not in here, no. College geometry. Okay. So maybe some calculus. But that's kind of the idea. That's why we are finding the sum of the interior angles, because it's going to be necessary for us to set up our next level of problem. Now, the other thing we can work with are the exterior angles. And this is kind of interesting. A plus B plus C is what? This is a triangle. A plus B plus C is 180. All right? Now, each of these X, Y, and Z are the exterior angles of the polygon. An exterior angle is found by extending the side of the polygon and then matching it with an interior angle. I could do it either way. I could extend this side and get this exterior angle over here, but these two angles have to be congruent because they're vertical, yes. So it doesn't matter when we calculate exterior angles, we only do one per vertex. One or the other one, they're going to have the same measure, so it doesn't matter which one you choose. But what would the sum of A and Z be? How about B and Y? C and X? So if I do A plus B plus C plus X plus Y plus Z, so I add all those together, I get 180 plus 180 plus 180, which is 540. Right? But A plus B plus C, we already know, is 180 plus X plus Y plus Z equals 540. So if I subtract 180 from each side, I get X plus Y plus Z equals 360. So the three exterior angles added together don't add up to 180, they add up to 360. That's in a triangle. What happens in a quadrilateral? Well, let's figure it out. I've got A, B, C, and D. A plus B plus C plus D is what? 360. Okay, so I get W, X, Y, and Z. W plus A is, so I've got 180, 180, 180, 180. So how many 180s do I got? 4 180s, so that's 720. So all the pairs, A plus B plus C plus D plus W plus X plus Y plus Z is 720. But this much I know is 360. And if I subtract 360 from each side, I get W plus X plus Y plus Z equals 360 again. How about a pentagon? Well, let's just shortcut this a little bit. If we do the interiors, A, B, C, D, and E, then we know that's 540. How many interior-exterior pairs do we have here? 5, and each one is what? 180. 5 180s is 900. So 900 minus the 540 leaves us 360. So the exteriors always add up to what? The same thing, which is 360. So the sum of the interior angles is always changing depending on the number of sides. The sum of the exterior angles is a constant, which means we have a different way of finding the measure of each interior angle, if we like. Rather than finding the sum, let's go back to my nonagon here, okay? That's my 9-sided polygon. Well, what's the sum of the exterior angles here going to be? 360. And since all of them are the same, each individual one would have to be 360 divided by 9, or 36 divided by 9 is 4, so 360 divided by 9 is, my clock's going crazy. Squirrel. Okay. Zombie apocalypse?
No, we're going to die.
Zombie apocalypse.
No.
Okay. So each exterior angle has to be 40 degrees. Well, if my exterior angle here is 40 degrees, what's my interior angle have to be? 140 degrees. Because I have to add up to 180. You're wounding my soul. Okay?
Well, it's kind of hard to wound something you don't have.
It's there. It's just dark, cold, and black.
I realize.
Remember that. Just like your heart. Okay. All right, so that's what we're doing today is working with interior and exterior angles of polygons. That's all this assignment is. And no, it's out of the book. And then we're going to use that now to help build and solve our polygon areas. And we've been kind of building up to this whole setting up the triangles and solving the triangles thing for some time now. We've been kind of going over this and over this and over this. So really, what we're doing the rest of this week, solving the areas of polygons, should not be shocking to you in any way, because we've been preparing you for this. I've been talking about this is how we're going to use this triangle stuff. This is why we need to know our triangles. I've been giving you examples of it. We've actually gone through and solved examples of this. So when we do this tomorrow, it should be, yeah, I've seen that before. I got an idea what's coming. You should pretty much have the idea that this is exactly what we're going to do with our polygons. We're going to solve the triangle, the right triangle inside the isosceles triangle inside the polygon. And we're going to break it down, and we're going to build it back up. And that's where we're going to do it. That's how we're going to solve these things. That's going to be our formula. That's going to be our trick. So, your assignment, page 510. So we are going back. Problems 3 through 21 and 23 through 26. They should be fairly easy. And then we're jumping up to chapter 11, section 6. And we've got this wonderful word here called the apothem of a polygon. Some people say apothem. I would say apothem. That sounds like an opossum with a lisp. Apothem. I know. I learned that one too. Okay? No. There we go. There we go. All right. So there's your assignment.